So now we're going to start section 13.8, which is about extrema of functions of two variables. So I want to start by recalling extrema for a function of one variable. So we're going to recall what you saw back in Calculus 1 when you discuss extrema. So let's say I have a function here. It looks something like this and that and that. Okay? Then this point up here was called a relative max. And this point down here was called a relative minimum. Relative just meant locally or nearby, that point was a maximum or a minimum. But you also discussed focusing on an interval A to B. So I'll say if we focus on an interval A to B, we can talk about absolute maximum and absolute minimum. So there, when we're focused on an interval, we're going to talk about the maximum value on that interval and the minimum value on that interval. Okay, so we're going to have some of the same things going on here with a function of two variables. So let's consider a continuous function f of two variables. So z equals f of xy, defined on a closed, bounded region R in the xy plane. So here, remember that your function is of two variables, and so when you graph this, you get some kind of surface in 3 dimensions. Okay, so we have x, y, and z. And remember that your domain lies in the xy plane. So here I'm taking a region that's closed and bounded in the xy plane. So here, just imagine I'm taking like a square, and I'm looking at the portion of the surface that lies above the square. So maybe my surface does something like kind of like that. It comes to a point. Let's see if I can make this a little bit better looking. It comes to like a point like that. And so here, this would be your largest z value. So this would be your maximum. Maybe this point here, this would be your lowest z value in that entire region, and so this would be your minimum. So why do we even have to have, minimums and maximums? Do we? Well, that's the extreme value theorem. It tells us that there is at least one point in R at which f takes on a minimum value and there is at least one point in R at which f takes on a maximum value. So this theorem guarantees that I have a maximum and a minimum value over this when I'm restricting myself to this region R. So you can think about this as saying you have an absolute minimum and an absolute maximum. But we also have relative extrema. And so remember, relative extrema mean they are locally or nearby a minimum or maximum. So I'll formalize that now. The function f has a relative minimum at a point x naught, y naught if f of xy is greater than or equal to f of x naught, y naught for all xy in an open disk containing x naught, y naught. So nearby, what this is saying is nearby this point x naught, y naught, your function outputs values that are at least as big as your point x naught, y naught. Okay. And then you can define a relative maximum in a similar way. The function f has a relative maximum at the point x naught, y naught if f of xy is less than or equal to f of x naught, y naught for all xy in an open disk containing x naught, y naught. So again, it says that your point x naught, y naught is a relative maximum if nearby your function outputs values that are not any bigger than what I get when I plug in x naught, y naught.